Good morning, everybody. Today we have an educational Codeforces round. This is educational round 102. I'll be competing in this video, and then at the end of the video, I'll share my thought process for all the problems that I know how to solve. So let's jump right into the contest. We've got Eclipse here. We should be ready to go. I guess we don't really need this part of my template anymore, but anyway. You've got an array of n elements. All of them are positive integers. In one step, you can choose 3 indices and assign the sum of the second to the first one. Can you make all AI lower or equal to d using the operation above any number of times? Are all of the elements positive? Oh, assign it. Yeah, okay. So you just care about the 2 things after you. Yeah, okay. Sounds good. Let's make some bigger text for you guys. Multi-test case, int n equals this, cap equals this, int array a, read array size n, and then for int I equals n minus 1, greater than or equal to 0, I plus plus, m2 equals an integer.max value. All right. Well, val equals max.min of val m1 plus m2. If val is greater than or is less than m1, then m2 equals m1, m1 equals val. Else, if val is less than m2, m2 equals val. If val is greater than cap, then sys out no and continue outer. So this will be our outer loop. We'll go to the next test case. Otherwise, we'll sys out yes. Crashed. What's up with this? Oh, I minus minus. This third one is yes. Oh, they can be any of these, I see. Okay, well, let's just do this then. I equals 0, I is less than n, I plus plus, and then, what did I call this? Ruffle sort. Yeah, looks good. So there's a cleaner way of implementing that. I thought I had to be less than j and k when I first read it. But I think this should be fine. Okay, 0 says we've got it, so we can move on to B. Let's define a multiplication operation between string A and positive integer x. So you write x copies, just like in Python. String A is divisible by another string B if there's an integer x, where it's that. Okay, I see. Not divisible by AA. The LCM of 2 strings is defined as the shortest non-empty string that is divisible by both. Given 2 strings, find the LCM or report that it does not exist. So this is BABA, AAA, ABA. Oh, weird. It's kind of ugly, I guess. Oh. fine. We'll restart Eclipse now. Okay, so the idea, we can like, the number of times the first one will occur will be between 1 and 20. So if we try that many copies of the first one, it'll definitely work for the first. We just check if it works for the second. Yeah, that's the idea. So that should be pretty quick, I think. Okay. Char array A, fs dot next to char array. B is the same thing. Char array result will be, well, okay, so let's say 4 int n times equals 1, n times less than or equal to 20. Okay. Or I is less than res.length. Okay, and now check if it works. So if 4 int I equals 0, I is less than res.length, I plus plus. If b at I mod b.length is equal to res at I, well, if it's not equal, then continue times. This will be our times loop. And then otherwise, if they all work, then sys out res. This should be res. Yeah, and then sys out just 1. And then continue outer. Yeah. If res.length mod is not equal to 0, then continue. Okay. So we just check all of them. Is this right? Should it be 6? Should be 6. I didn't see that one coming, but that looks good. So let me quickly explain why this is going on. So some of you may have noticed I'm not able to type mod, or like I've been really bad at it. The reason for that is here we go. I replaced the keycaps on my keys, so now I have no letters. They're all just like blank, which I think looks really cool. But the downside is I don't yet know how to work with that because I haven't memorized the mod keys. So there's that, yeah. But just in case Russia has like a crazy keyboard, I need to have them memorized. So that's why I'm teaching myself that, because for World Finals in Portugal, Portuguese keyboards are kind of wacky. But anyway, enough about that. We have a sequence of n elements. That's just 1 through k repeated. Is n going to be huge? Oh, no, okay. Oh, so it's 1 through k and then 1 through k up to a second time. Let's call an inversion a pair of indices such that, yeah, okay. Suppose you have a permutation of size k. You want to build a sequence B of size n, where B of I equals the permutation of A of I. Your goal is to find such a permutation P such that the number of total inversions in B doesn't exceed the total number of inversions in A, and B is lexicographically maximum. Yeah, it sure can be proven. Thank you for not guaranteeing that, Voov. I appreciate it. Fantastic. Well done. We are making quite a bit of progress as a Codeforces community. I love to see it. Love to see it. Okay, so let's see. Maybe we could count the number of inversions initially. And we place the biggest thing we can at each step. Let's think about this for a minute. So let's suppose initially, somehow, we know the number of inversions. And then our numbers will be like 1, 1, 2, 2, 3, 4, 5. So if we place a 5 here, the number of inversions will be this. That'll be the inversions. I feel like there's an easier way of doing this, but I don't really see it. Okay, so that's 1, 2, 3, 4, 5, 6. This is 6 inversions. Originally, we had something that looked like this. Originally, we had 1, 2, 3, 4, 5, 1, 2, or 1, 2. So initially, this had 2 inversions. I guess let's count inversions backwards. This one had 5. This one also had 5. So the number of inversions is like n times like n minus k, or I guess k times n minus k. That's how many inversions there were. You get k of them for each of these elements here, and that's it. So if we're trying to maximize or lexicographically maximize this, 5 will give us 1 inversion for everything. Yeah, then we can just keep decreasing it one by one, right? So this gave us 6 inversions. We have 10 to spare. So if we try and place the 4, that would give us 1, 2, 3, 4, 5. So we can't place the 4, we can place the 3. Okay. So that gave us 4 inversions. So now we need 0 more inversions. So we can't place the 2, can't place the 2, we can place the 1. Place a 1. Or I guess we place, yeah, we place a 1. This gives us 0, then we place a 1. This gives us 0, then we place a 2, then we place a 2, then we place a 4. So we place some suffix, then we place one element somewhere, and then we place them in order of what's left. So we can do it in linear time. I guess I'll sort it'll be n log n, but you could do it linear because your sort is going to be very constrained. Okay, yeah, it doesn't have that many solves, which makes sense because it's more weird. It's not really difficult. It's just weird. It's like a weird problem. I wouldn't say it's bad. It's like kind of a it's whatever. It's not like amazing, but I wouldn't say it's a bad problem. It's an early difficulty jump for sure, though. Sum is still pretty small. Okay. Int n equals this. K equals this. Int array a equals new int array n. A at I equals 1 plus I mod k. Good, so we have our array. Long and inversions equals k times n minus k. This needs to be a long. Good. All right, so now we have however many inversions. Now we need to maximize this. So let's make yeah. So let's do array list integer res array list boolean array used new boolean array of size n. Then we need the indexes. Okay, fine. So pair. So yeah, we need the indices so that we can sort this. So this is going to be a pair array, really. So the value will be the same thing as before. The index will be I. Now we can call arrays.sort on this array. So now we'll sort the pairs. That way we can look at the indices to print our answer. We'll also just make this arrays pair. And at the end, we want to print this. So for pair p in res, out.println p.index plus a space. Shouldn't be print line, should be print. Then we need a print writer because there's lots of output. We need to close it at the end. Okay, so now we just need to figure out what the actual answer is. Very good. So we have these sorted by value, which means we want to decrease. We also need the number less than each thing. I equals, well, for int, I guess for pair p in a, frequency of p dot value plus plus, int array n less than, new int array, I guess this is just cumulative sum, right? The definition of cumulative sum works very well. Okay, so now what do we do? Yeah, we go from the end. So for int I equals n minus 1 greater than or equal to 0 minus minus. Okay, so if this is, or if we can afford this, so int cost will be cumulative sum at I. So if cost is less than or equal to n inversions, then we will afford it. So then use did I equals true n inversions minus equals the cost, because we need to use all of these inversions. And then we need to add this pair to our list. Okay. So that's very helpful here. Otherwise, we can just skip it. All right. So now for int I equals 0 less than n, I plus plus. If not use did I, then res.add 8i. Now we should have n things, and then we should be able to print all of them. Int plus 1. One, two, one. Ah, really? Okay. So this should be, okay, we don't need this. Two, one test case. The number of inversions should be 0, right? Because the array is just 1, 2. So then, yeah, if we do anything else, it won't work. Okay. Yeah, so the cost isn't CS at I, it's CS at A at I dot val. Is this right? Yeah, it is. We need to sort this though. We did sort it. Good, I think we're fine. 1, 1, 2. 3, 2. Wait a minute, what? Okay, never mind. Permutation of size k. That's why we make sure we understand the problem, ladies and gentlemen. We have to build this. This is the second time in 3 problems that I've done that. Yikes. And this spent a lot of time too. Okay. Hard set. We've got an okay. Permutation of size k. We want to build a sequence B of size n. Oh. We want to find P. Find a permutation P such that the total number P is of size k. Got it. So we're rearranging the order of these elements and of these elements. I see. Okay. Try again. Okay, so I solved completely the wrong problem. Not even close. I guess that's one cost of like going super fast. Sometimes you just totally miss. But anyway, 1, 2, 3, 4, 1, 2 is some example. So we could have something like 4, 1, 2, 3, 4, 1. How many inversions do we create here? We have 1, 2, 3, 4. So this one has 1, 2, 3, 4. I guess let's do from the 4. So it's got 1, 2, 3, 4. 4 has 4. These pairs are all broken, and these pairs are all broken. Or those two are also broken. So there's 6. Does it matter? Okay, so if k equals n, then the answer is you need 1, 2, 3, 4, etc. What if k equals n minus 1? So now if we have like 1, 2, 1, this gives us 1 inversion. If we have 2, 1, 2, this also gives us 1 inversion. Okay, what if we have 1, 2, 3, 1? Then we have 2 inversions. We have 2, 1, 3, 2. 1 inversion here, 1 inversion here. Then we also have 2. And then what if we had 3, 1, 2, or 3, yeah, 3, 1, 2, I guess? 3, 1, 2, 3. Then we have 2 inversions. Okay, what about 3, 2, 1? Well, now we have 3 inversions, which is not going to work. Can we just put the biggest numbers in the front? What? I'm still misunderstanding the problem. What? Beta I equals... Oh! Ugh. It doesn't go from 1, it goes decreasing again. Okay. Try number 3. Man, this is... oof. Okay, so I'm just like totally... this is all wrong. Okay. Okay, so let's do some examples here. So if n equals k, well, let's say, what does this look like in general? So 4. So we have 1, 2, 3, 4, 3, 2, like this, for instance. So this gives us 3 inversions. This gives us 4 inversions. So it's n minus 1, n minus 2, etc. n minus 3. So we can put the 4 in the beginning, right? What does this cost us? So then here, oh, maybe that's more painful. I don't know. Okay, so these 1, 2, 3 pairs. So this would be 3 plus 4 equals 7. So there's 7 inversions here. Here we have 1, 2, 3. This 2 gives us 2. This gives us 1. It's too big. So what if all we did were swap? Well, if we swap 2 numbers, we just create an inversion. Or we just create 1 inversion. So that's a good way of looking at it. Then we'll have a proof maybe. So if we swap these 2, then we'll have 4, 3, 4. So this doesn't actually create anything, so that's fine. We'll do that. What if we swap the 4 and the 2? Then we have 4, 2, and 2, 4. So again, we didn't create any inversions. If we swapped the 4 and the 1, that would create an inversion. So then we'll want to swap the 3 and the 2. So then we have 1, 4, 3, 2, 3, 4. So we get the last n minus k and reverse them. 3, 2. So 1, 2, 1. Yeah, so swap these. Okay. So how many things are there to swap? Yeah, so this is the last one. So we swap n minus k. Yeah, okay. So let's just math. This is an easy problem, man. It's an easy problem. This is just, I went to the moon and back trying to figure it out. I don't know why. Okay. Anyway. So we have an inner array of size k. Okay, so now we just have to figure out how many we reverse. One plus n minus k. Need to reverse this many things. We go through half of them. Int temp or int l equals start int plus I. And then the r will be end int minus I. Int temp will be a at l. A at l equals a at r. A at r equals the temporary variable. So we just reverse that many things. There's probably a cleaner way of doing that, but who knows. We're good. Okay, and we crash. What do we crash? Index 2. One, one, two. Just reverse two things. Yep. So this is start index 0 and index 1. 0 less than 1 plus plus. L equals 1 minus 0. Yeah. Yeah. Yep. Start index 0 and index 1. Or wait, what? Oh, this should be K. This should be K as well. Okay, I think that's probably right. Okay, so there was not a difficulty jump. I just thought there was. I don't know why. And that was a good problem. It's just very rough. Okay. Yeah, long story. Anyway, problem D. The tough part is reading, not actually solving the problems. Learning how to read the English language is tricky. You're given a program that consists of n instructions. Initially, a single variable x is assigned to 0. Let's slow down here a minute. How about we do that? Initially, we have a single variable x that's assigned to 0. There are two types of instructions: increase x by 1, decrease x by 1. You're given m queries of the following format. How many distinct values of x, how many distinct values is x assigned to if the instructions between L and R are ignored and the rest are executed without changing the order? So how big does it get and how small does it get? Yep, so some prefix, how big and small does it get? For some suffix, how big and small does it get? So the prefix is easy. Yeah, because for each prefix we can store, like, we do a bunch of operations, right? It's the same as like a bracket sequence, I guess, but I don't know, not really, whatever. We store, like, it starts at 0 and then it follows some chain, right? Maybe it goes like this. So this is what we care about. We care about the maximum, the minimum, and where it ends up. Then when we have some suffix, I guess we care about the same thing, right? Yeah, we care about this, the maximum and the minimum. And then if we plug these two together, then we have a new maximum maybe and a new minimum maybe. Yep. Okay, let's do it. Okay. Int n equals this, n queries equals this, array line. So int array max, min, end. We want the same thing in reverse. So this will be, I guess, after processing. Oh wait, how do we do this? Yeah, +1. Okay. So cur plus equals line at I equals a plus 1, otherwise -1. Cur max equals max.max. Cur max and cur min will be the minimum of the cur minimum and the current. Max at I equals cur max, min at I equals cur min, end at I equals end, or equals cur value. And now we do the same thing going backwards. So cur max equals cur min equals cur 0. -1 to 0 going backwards. Okay, so those are all the same. These should be reversed. And I think that's it. Yeah, okay. These should be all +1 because there's index 0 where we haven't done anything. But these shouldn't be because index 0 we should have done it. Good. Yep, alright. Cool, so for int QQ0, QQ is less than number of queries plus. The number of queries can probably be pretty big. So we need print writer. Out.close. Now int L equals this, R equals this. Okay. Let's make these 0 indexed. And then to make things easier on ourselves, well, yeah, okay. So int max equals max at L, min equals min at L, cur equals cur at L. Get that. Oh, can we not? Oh, we can't do that. Yeah, okay. So that's going to be our answer, however many values it hits. Okay, so then we need the difference. So int difference will be, we don't want to increment or subtract 1 from R because we delete L to R, right? Yes, yes. Between L and R inclusive. Yeah, so we don't subtract 1 from R. The difference will be the end at L minus end at R. Voice crack. End at L minus end at R. End at R minus end at L. No, n going forward at L minus n going forward at R. No, we want to line them up. We want to line them up. Yeah. So end at L, and then end reverse at R. These two should be equal. So we need to move down by this amount. Okay. Int post max equals max reverse at R minus diff. Okay, I think that's right. Lots of stuff. 1, 1, 3, 3. No, okay. If you delete 2 to 8, you should have 2 values, right? Yep, I'm saying 3 values for some reason. Oh, this isn't right. Oh, I guess we don't need it. Premax 0, premin -1. The difference is -1. Shifted down by -1. Interesting. Yeah, we should need to shift it up by this, so this should be plus. One, 2, 3, 4. 1, 2, 4. Okay, example 3. 2, 5. So we delete from 2, 3, 4, 5. So minus, 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 plus. Okay, let's write this down here. So we've got minus and then minus, minus, plus. So premax is 0, that's right. Premin is -1, that's right. The difference should be +1. Why is the difference 0? Oh, yeah, it should be 0, okay. Then this is +1. Because that's not how it works. Is that why? Yeah, let's look at this for a minute. We're interested not in this amount, but in this amount here, and this amount here. Yeah, so we got to look at these values. Okay. So this is going to be end L plus max R at R minus cur R at R, or end at L. This is just end R. I think this is the same for the mins. This is -1. The minimum R, well, end R is -1. Yeah. Min R, so I guess this will be 0. So what does this look like? It looks like you go down, and then from the right we go up, down, down, up, down, down. So if we line these up, this is 0, this is 0, -1. So this should be 2. Two, 5, there should be 4 values in minus, 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 plus. Oh, yeah, I guess, because these aren't actually down, these are up. That's kind of wacky. Okay, surprise. Guess that's part of going backwards, right? Alright, let's see if we got this right. Didn't see that one coming. Man, I'm kind of struggling today, to be honest. Like, this is harder than I thought. 1, 2, 4, 4, 3, 3, 4, 2, 3, 2, 1, 2, 2, 2. Okay. Okay, so we don't need this. Why don't we need this difference? Because we're not using it. Yep. Okay. That was messy. Okay. Yeah, I'll explain that at the end with a picture, though. Hopefully that'll be more useful. Oof. On to problem E. We'll listen for our result. Okay, we got it. Surprisingly, we're not doing that badly, I guess. But that's fine. Yeah. Monogon has E, and Monogon blazed through this, so I guess we're just slow. Minimum path. You're given a weighted, undirected graph of n vertices and m edges. Okay, I think I can read that part correctly. Weighted graph, that's it. Okay. no self-loops, and no multi-edges. Let's define the weight of a path of k edges with indices these things as the sum of the weights, minus the maximum of the weights plus the minimum of the weights. Is this just the sum of the weights, or are these included in the formula? I think it's just the sum of the weights minus the max plus the min. So what is max minus max plus min? What does that mean? It's like the range, right? So it's the sum minus the range. So all things being equal, wait, what is it? Find the minimum path from the first vertex to the ith vertex in the set. So we want to find, yeah, okay. So all things being equal, we would like to minimize the distance. And in addition to minimizing the distance, we want to maximize the range of the distance. Like maximize the range, okay. Gotcha. Let's think about that for a moment. So what is the distance to this? You can get 6 minus 0, or you can get seven minus 5. So the distance here is 2, really. We got a Cliff Bar, but I'll be right back. right, so let's draw the sample here. Six, 1, 1. So we need 5, 4, and 2 need to be connected. So 3, 3, 2, 5, 1. All right, now let's just go through and connect them. 4 here. So 5, 4, with weight 2, 4, 2, with weight 2, 6, 1, 5, 2, with weight 1, 3 and 2 with weight 3, weight 4. Distance from 1 to 2. You can do it with a path of length 2. My guess is it's this path here. So 5 minus 3, yep. You can also do it with this path here. So suppose we know what the smallest. Yeah, okay. So like the reason this problem is tricky, we can't just run Dijkstra's, is because like we only get this benefit once. So we can't like add, we only get to subtract the difference once. So that means we can't like factor this into the cost of the edges, because Dijkstra's is like the sum of everything. So if we have a bunch of big edges, it depends how many we use for how much each edge gets this benefit of us subtracting the range that we use. So we're gonna need to like modify something or do something. Yeah, we're gonna need some sort of modification here. But let's think about this for a minute. So let's say we knew the minimum. Dijkstra's is tricky because it's already n log n, right? It's kind of hard to do online, I think. What if we knew the minimum? Then the cost is the sum minus the max. Alternatively, if we know the max, then we get that max for free. But we don't have to use it, so it's probably easier if we brute force them in. So we have to pay them in a second time, and then we don't have to pay for the max. So we want like online Dijkstra's, but max edge along path is free. Can you do online Dijkstra's? Is that a thing? We still have like a bunch of things we need to update. Even if we had like an online Dijkstra's, we wouldn't know what to check. It also seems like a very difficult algorithm to implement. What if we like run Dijkstra's and then try augmenting it or something? Like we have some path and then we try and say, can we improve this path by finding some other node that we hit that would increase the range somehow? So some edge will never be negative. We'll never actually have negative cost. At best, it'll be like free, right? Yeah, all the weights are positive. So it's always going to cost at least as much as the minimum. So what if we just do Dijkstra's from here? Which edges do we expand? We expand this edge, but it's like a 1. So the minimum is a 1 here. Expand this edge. We wouldn't expand this. Say we expand, say this to make things interesting. Then this. Then this maybe. So there's our Dijkstra tree. Can we just modify Dijkstra's? Is that it? Restore the state we came from? That feels sketchy. Why would that work? So the state would be the min but like there might be different maximal things that you care about. So I guess the thing that we should ask is like, what would we care about? We might want to minimize cost. We might also want to minimize max minus min plus cost. Might also want to minimize max, but also have cost. Yeah, so this is out, but there's like some mask of these, so like, this is tricky. Four versions of each node. Yeah, I think that's just it. That seems like it would work. So we have to add this and subtract the max. So this we want to do correctly. So that should be fine. We can leave that alone. The issue is the min. How do we avoid... Wait. We get to pick one thing that we have to double count. We get to pick one thing... Oh, we want to do this correctly too. Like the thing that we would double count would be the smallest. The thing we're going to overcount will be the biggest. Yeah. Okay, yeah, so we just add each edge multiple times, and that's it, okay. Is problem E? Good. Okay, we'll get this. How's that gonna put us on the scoreboard? Not great, not great. Pretty bad, actually. Are we 2 hours in? Oh, this is a 2-hour contest. We're like an hour 15 minutes in, so not that bad, okay. Yeah, that's fine. Well, oh well. So what do we need? Static class node, array list edges, new array list. We need a static class edge, and then static class state. State will have a long distance, and then a node at. Okay, edge will have a node 2 and a long cost. Then a node has an array list of edges, also a long dist, which is initially, well, yeah, long dot max value, I guess. Good. So now, multi-test case, right? Single test case even. Nice, okay. Int n equals this, m equals this. Node array nodes, new node array n times 4. Okay. Then we do Dijkstra's, right? Well, we'll do Dijkstra's in a minute. How about that? Wait, is it just normal Dijkstra's? Because we can work the cost into the edge. Yeah, just normal Dijkstra's. Okay. So let's write the Dijkstra's now so we don't have to think about it. We're going to have used min, used max. Okay. All right. Priority queue of state PQ equals new priority queue nodes at 0 dot dist equals 0 q dot add new state nodes at 0 distance 0. Do I have those in the wrong order? I do. Thank you, Eclipse. Appreciate it. Then, while not pq dot is empty, state next equals pq dot remove. If next dot dist is not equal next dot add dot dist, continue. Edge e next dot add dot edges. Long new cost equals next dot dist plus next dot add dot or next dot plus e dot dist or e dot cost. Okay. Node 2 equals e dot 2 if new cost is less than 2 dot distance, then we want to reset this, so 2 dot dist equals new cost, and then pq dot add new state to node, or the cost will be new cost, and it'll be 2. Keep doing this till the end. Okay. Print n-1 integers, so we need a print writer again. Okay. I equals 1 less than n, I plus plus, out dot print line. Nodes at I dot distance. That's what we're looking for. No print line, print plus a space. And then out dot close. Why am I missing a close curly brace? I'm not. Okay. Good. So we just have to build our edges now, so this should be easy. So for each edge, we want to know where it goes from, to, and its cost. So then we want to do this 4 times. Okay, so is it undirected, they said? Okay. Oh boy. Nodes at from dot add or dot edges dot add new edge nodes at 2 and then base cost. Same thing backwards. To from. Okay. You can also Yeah. So we want to do this for each of the 4 groups. So within each group, you can take the edge. That's fine. Where is this error? Okay, so that's good. You can also cross groups sometimes. So you can take the min or the max or both. Make an add edge method. Alright, so we can take the min here. So add from to, from plus 0 to 2 plus, oh, this is one way. See, I would want to call this by, but rainbows, you know. Can't have that. Okay. Yeah. Okay, so then this will be true. This we want to add from plus 0 times n to 2 plus 1 times n. The cost will be base cost minus the base cost, or no, plus base cost, because we pay them in twice. Yep. Nodes false. We can also take the min here from going from 2 to 3. I plus 3 times n. Yeah, okay. Then we can take the max here. So this is free, and we go up by 2. Take the min or the max, or we can take both. So we can go from 0 to 3. And what happens then? We just pay the cost. Minus base cost plus base cost. Again, single directional. Does this work? Nope, not even close. Why would that be? Let's draw out the graph. Man, yeah, we are really doing terribly. We're not going to solve 2 problems today. Yikes. Getting pwned by the set. Alright, what does this graph look like? 5, 3, 4. Two, 1, 1, 3, 2, 2, 2, 4, 2. 1 to 2. This should cost 1. Yeah, why am I saying it doesn't? So I'm looking for, what edge am I looking for? It should be, I want the edge from 1 to 2, right? 1 to 2. So this will be 0 to 1 plus 3 times 5. So that's 3 times 7, 15, so 16. 0 to 16. Can I not subtract 1 from these or something? Oh, but backwards. So 16 to 0. Oh, because these are all gross. Okay, well, thank you for letting me know at least. To from, or this is also to, these are both from. Okay, and then 1, 2, 2, 4. Good. This TLEs, I'm going to be very upset. I guess I'm adding a lot of edges, but still. What's my time limit? 3 seconds. That seems a bit tight. What's the bounds? 2 times 10 to the 5th. Uh-oh. Do not TLE on me. I'm using a priority queue. Please, please don't TLE. What do I do with TLEs? I don't want to switch to C++ today. I'm not in the mood. Really not in the mood. Oh no. Oh no. Oh. You're kidding me. This is obnoxious. This is actually just obnoxious. Ugh, so annoying. Are there any of these things that we don't need? Can make this an int list. This feels like it's the intended solution too. Java is the worst. Okay, is the problem that I'm using too many objects? We can get rid of these edges. Maybe that'll help. So this will be an array list of node to an array list of integer cost. This part is linear though. This is the n log n part. Okay, well, we can try it. I guess this is always an integer, right? Fine. we not have just made this a 5-second time limit or something? Anyway, next dot, okay. Next dot at, yeah. This edge will be oh, 2 will not be next dot. It'll be next dot at dot get or dot 2 dot get I. And this will be next dot at dot cost dot get I. Dot cost equals array, and then dot cost state size. Or cost dot length equals, and then dot cost equals, and then dot get I. This is a mild improvement. I think we can, if we need to, we can improve the state a little bit. Yeah, I think we can improve this a bit. I'd like for this to just pass, though, to be honest. Are any of these unnecessary? No, they're both. You need both of them. Yeah. We're dealing again. Okay. Just 31. A little bit better. we do here? So the state, this needs to be an int at. Okay. This is 0. Node at equals nodes at next dot at, I think. Okay, then we can make this to be something different. What is this? Oh, new int array. Okay, so that's mildly helpful, I guess, right? Now this is all a node is. So now we have a simplified state. So we can combine the state. Ah, this is the worst. This is actually just terrible. Why would we need to do this? Okay. Okay, so this is E2. Let's make an E3. So here we need a static long array. This is state costs. Static int array state nodes. New long array. Out of the 7. Goes to int array. 7. Should be fine, I think. And then this can be a priority queue of integer. Zero. Static int state at equals 0. State costs at 0 equals 0. All right, state ID. State nodes at state ID equals 0. State ID plus plus. Int next equals pq.remove. Why does Eclipse do this? How does Eclipse not have this figured out? Okay. Return long.compare state costs at A, state costs at B. Okay. Good. State nodes at next. Ah. equal to add.dist. Okay, state nodes at 2 equals I think the next optimization from here is write our own priority queue, but that's going to be cancer. We're wrong. I don't want to have to deal with this. This is obnoxious. This is actually obnoxious. Okay. What the heck? Is this right at least? Did I make a mistake here? Okay, so there was a translation error. State nodes, state cost, and state ID. So compare the costs of the two. That's what this had previously done. Compare the two distances. Okay. Distance equals state cost. Well, I guess we should try and just submit this. What did I change for this? What did I optimize? I got rid of, yeah, these changed to this. I can try this. This is just E, right? Yeah. Oh, maybe I should be submitting in Java 11. Okay. Anyway, we made a bug in converting it. And all we did was make these global. All right, I'll go to the bathroom, be right back. Yikes. Rough set. We're getting worse over time. Maybe we're just like super close to the limit, I guess. So why can we not convert this? Oh, this should be next. I think that's the bug. Okay, so well, we have that. We have to write our own priority queue now, right? Oh, maybe these are too big. Or maybe it's crashing. We never know. Just 9. Oh wait, this was 10 to the 7. Yeah, that's probably too big. Is this too big as well? Seemed a little faster. So we'll just spam some submits because I don't think we have time to write our own priority queue. Getting a little dangerous here, how low these numbers are getting. I don't know that I feel comfortable with this. I feel like this is hackable. Yeah, we need priority queue. What objects do we have? We have these nodes, we can't really get rid of them. I guess we could get rid of them actually, but there aren't that many of them. States are the real issue. We're not even using these. Yeah, we have these integers in the priority queue. That's it. Ah! So annoying. How do you do priority queue? You just need to change yourself and your parent, right? You just swap yourself and your parent if you need it. There's no way this isn't intended. Is it TLE? Wrong answer. How did they not see the fact that the time limit on this was going to be crazy tight? I don't know. Oofda. I'm a blue level today, it looks like. Yeah, I don't know. I guess we'll go over solutions. This was kind of infuriating. My Dijkstra's wrong. Let me... Yeah, we set the new cost of the node to this, and then we check if it's not equal, we continue. So the Dijkstra's isn't n squared. We're just failing here. So, yeah. I'll do this after the video, and then I guess you can check Codeforces to see if it passes. Unless there's just a better way of doing this, but how many nodes am I creating? I create 4 times n nodes, and 4 times n, well, I guess really 8 times n. Where's the times button? Where's the times button? Okay, 8 times n plus 10 edges, plus 10 m edges. So I guess 18 m edges. Yeah, that's a bit much. I guess that's a lot for an n log n. Maybe you can do a constant factor less. This is 8m, and this is 10m. So I have, my runtime is 18 times 2 times 18 times log is like 17. Yeah. Should be fine. I guess the log is more like 20, but still, it's like 10 to the 8 runtime. Oh, I'm looking at the wrong problem. What are bounds for E? 2 times 10 to the 5th. Yeah, yeah. I guess maybe it's just an integer issue. Annoying. Very annoying. Alright. Well, I'm smaller today than usual. Hello. Anyway, we'll go over solutions to all the super easy problems, I guess. Cool. So, problem A, replacing elements. You have an array of all positive integers. In a given step, you can choose 3 distinct integers and assign the sum of one to the sum of the other 2. So there are like 2 possible cases here. Let's look at the smallest 2 elements. So if the smallest 2 are both like let's say the min 2 elements are a and b, then if a plus b is less than the limit, I think they call the limit d. If a plus b is less than d, then it's possible. Because we know both a and b are less than d themselves, and we can make everything else equal to a plus b. So then the answer is yes. If a plus b aren't, that means there aren't any 2 numbers you can add that'll make some other number be small enough. So you never use the operation. Then you just check, are all elements under D? And that's the answer. My code for that is a bit messy because initially I misread it. Initially I thought it had to be IJK in order, but that's not the case. So yeah, but I store like the minimum 2 elements in the array when it's sorted. So the first 2 elements just wind up being the first 2 times this for loop runs. And yeah, I just keep track of them as I go. But anyway, yeah, that's just a slightly different problem. So like this works, this solves that problem, but it was like initially written on a misunderstanding and then modified afterwards. Cool, that's problem A. It's pretty easy, hopefully. Hopefully you're able to get it. Otherwise, you should definitely upsolve it. For the second problem, string LCM, it's a bit implementation heavy, I think. I guess not too bad. But the first observation with LCM is that just like with numbers, the LCM of these 2 strings, the maximum length it will be is the product of their lengths. Because if the product of their lengths works, then that's your answer. But if it doesn't work, the reason it doesn't work is going to be like because you'll have 2 characters that don't match up. So if you make it any longer, let's do an example here. Let's say 3 and 4, right? So this is 3, 3, 3, 3, and then the 4 will be 4, 4. Oh wait, how does 4 work? We should have 3 of these should be equal to 1 of this. So like that. Yeah, there you go. Yeah, cool. Yeah, so here, this is, their LCM will be here or before. And it's really just the LCM of the 2 lengths. So we can like brute force the number of copies of the first word we have, because we know if there is an answer, it has to be divisible by the length of the first word. Since we know the length of the second word is at most 20, the biggest this will be is like 20 times like length of A, or length of word 1. So yeah, we can brute force all of them, and once we have it, we can literally just fill in what the answer would be. Because we know, like, if this is ABA, for instance, then we fill in ABA, we fill in ABA again, ABA again, and then ABA again. And we just have to check, if we filled in B, would it make the same word? So in this case, if B is like ABAB, oops, this is A, B, A, B, A, B, A, B. Clearly, it doesn't work. We've got a mismatch here, and then a bunch of other mismatches later on. But yeah, so it doesn't work. So that's the idea. You can just brute force the length, make that of the first word, see if it works with the second word. That is, I guess, maybe like the only problem in this set that I did right the first time. But here's what it looks like. You have this array for A, this array for B. You brute force the number of times you make a copy of A, and then res is just A, but this many copies. So we've got this this array. This constraint means this length that we're checking, it has to be a multiple of the LCM. Really, all you have to check is the LCM of the 2 arrays, and that should be enough. But yeah, here I guess I'm checking that it's a multiple of the LCM, because if it's not, then you won't be able to fit each string an integer number of times in it. And yeah, then I build the array and then check that it works with the second array. If it works, then I print it. Otherwise, at the end, I print -1. Cool, that's problem B. On to problem C. No more inversions. Okay, this array, or this problem took me like 3 tries to understand. It was a mess. Here's what the actual problem is. You have an array that looks like this. It's like A, B, C, D, C, B, A, or whatever. It's like some like palindromic array, except you might have some of the ends chopped off. So you might have something like this. Now the question is, we want to modify this array by changing which numbers we put in A, B, C, and D. So A, B, C, and D need to form some permutation, but the number of inversions in the array we create has to have the same number of inversions as it would if this were 1, 2, 3, 4, 3, for instance. So we don't want to increase the number of inversions. I think we're allowed to decrease it. Yeah, but we want the lexicographically maximal array. So we want the bigger numbers to be first. We want the first number to be as big as possible, of all ways of doing that. We want the second number to be as big as possible, etc. So here's the observation here. If we were to swap C and D, what that would do is we would get, like, the rest of the array would be the same, except we would have a 4, 3, 4 here. This doesn't create any inversions, because in both of these cases, there's one inversion. Initially, the inversion was here, but after this change, the inversion is here. So, yep, there's that. So now we have like 4, 3, 4. Very good. Now, we might consider swapping like this 4 and this 2, because we want to move the 4 up to be as early as possible. If there's no element here, if we don't have another B, then we can't do that, because if we swap a 4 and a 2, we'll create one more inversion. We'll have a bigger number before a smaller number, and the rest of the array will be the same. So we'll still have inversions between 4 and everything back here that's below than 4. We'll still have inversions between this 2 and everything over here that's above 2. But the only difference is right here we've added one additional inversion. So we can't do this without decreasing the number of inversions. And you can show that this is actually the minimal number of inversions you can get. There's no operation you can do in this array that'll ever decrease it, which means we'll never be able to swap this 4 and this 2. So everything before this hand that doesn't have a duplicate or isn't like the middle element, none of those elements can move. They're all stuck where they are. And then all of these elements we can move however we want. So these ones are locked, so we leave them how they are. And these ones, I guess I'll do another example. I'll do like one slightly bigger example. So it might be 1, 2, 3, 4, 5, 4, 3, right? So in this case, we can swap the 5 and the 4, because then we'll have 5, 4, 5. We just traded this inversion here, or sorry, we traded this inversion here for this inversion. Okay, so now we don't have that anymore. Now, if we swap the 3 and the 5, then we'll have 5, 3, and then 3, 5. So in this case, we've changed this inversion here for this inversion here. So we haven't increased the number of inversions at all. And then finally, we can swap the 3 and the 4. So then we'll have a 4 here and a 3 here, and then a 4 here. And in this case, we've swapped, initially we had, well, before this it was 3, 4, 3, right? So initially we had this inversion, now we have this inversion. So we still have 3 inversions, which is how many inversions we had initially. But we're able to freely move all of these elements. So we'll have them in like decreasing order and then increasing order. In other words, if you have some array that looks like this, 1, 2, 3, 4, 5, 4, 3, the solution is to just, like, we're only looking at this permutation here, right? So the numbers that we're allowed to move are these elements here. We'll just reverse this subset. And that's the solution to the problem. It's that easy. Oh, this is problem C. Yeah, you just reverse this range of the array. And that's it. All right, very cool. Then problem D. Believe it or not, this was the hardest problem I got, although it wasn't really that bad, but we'll see. Here's the solution to it. Or here's the problem first. You have n instructions. Each instruction is either a +1 or -1. So basically, let's look at this like visually. So we've got some graph. Maybe it increases, decreases, increases a bit, decreases like this. So maybe this is what it looks like. So we go some pluses, some minuses. Each one of these is a plus. Or this is a minus, sorry, excuse me. This is a plus, minus, 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 and plus. So we have some path like this. The question is, if we only look at all of these pluses and minuses, but we cut off some middle part. So imagine we cut off this part here, and then we took this, like this, and we glued it onto that. So that's what we're going to do. The question is, how many different numbers would we hit? How many different y values would we hit? Let's imagine we look at like this prefix here and this suffix here. Then we'll hit 0, 1, 2. This will be 2 still. Then we'll hit 3. So in total, we hit 4 different values, 0, 1, 2, 3. We're given this graph here. We're also given a bunch of queries. Each query is like keep some prefix and then also keep some suffix. The question is, how many things do you keep? So here's what we're going to do. We're going to have some path, right? We're going to have some path like this, and then we'll have some other path like this. We don't really know where these end up. They might end up at different places, but we want to imagine like gluing them together. So if we like do the math, what we'll figure out is the only things that matter are the highest we get in this prefix, the lowest we get in the prefix, and then where we end. And then for the suffix, we care about where we end. We care about the lowest we get and the highest we get. So if we know this distance here, right, maybe this is d1, and then we know this distance here is d2. This is the vertical distance between the lowest and the highest. So this is d1. This vertical distance here is d2. Then we can look at this prefix, right? So what we would do if we join these is we would have this minus d1. And this would be another maximum candidate. And then this plus d2 would be another maximum candidate. The other one would be a minimum candidate. So the things that might be our maximum would be in the prefix, whatever the maximum was. Also, this end plus d2. And then also the end minus d1 would be a minimum, and the original minimum would be a minimum. If we go from a maximum to a minimum, because we hit every value in between, we just hit the max minus the min plus 1. That's how many values we would consider hitting. Yeah, so that's the idea behind the problem. The math for it, you can definitely do more cleanly than what I did, but here's one way of doing it. So I had some debugging going on, but I did one sweep from the left where I stored what is the prefix max, prefix min, and the current prefix sum, and then the same thing for the right. When I say prefix max, I mean like the max prefix sum, not like the max of the ones and minus ones, because that would be kind of boring. Yeah, and then at the end, this is equivalent to D2, and this is equivalent to D1, where end R is the prefix sum from the reverse, right? The reverse prefix sum. Yeah. So equivalently, end R would be this vertical distance here from where you start to where you currently are if you go backwards. One implementation detail that caught me by surprise, which I guess makes a lot of sense, but I didn't see it coming, is when you go from right to left, if you see a plus, that means you actually go down a step, because that means the thing you came from before added 1 to get to you. So as you go left, you don't add 1, you subtract 1. So that's, yeah, watch out for that. I guess live and learn, right? So here you want to add 1 if it's a minus, and then subtract 1 if it's a plus. Cool. Yeah, then just basic debugging skills from there. All right, the last problem that I read in contest was problem E, and I can give you a possible, wait. Oh, yeah, I didn't solve problem E, but I can give you the idea that TLE's in Java, if you'd like that. Seems pretty intended to me, but I don't know. So the idea here is, the problem is run Dijkstra's. The modification, though, is the cost of a path isn't just the sum of the weights. You get to subtract out the difference between the maximum and the minimum value in the path. So let's say, for instance, you have some graph where the edges look like this. Maybe this is 5, this is 3, and this is 7. The cost of this would be 5 plus 3 plus 7 minus 7 minus 3. So this difference here is 4, so we get like 4 free points or whatever from taking this path. And then this sum here is 8 plus 7, which is 15. So 15 minus 4 is 11. And this part's 15. So that's the problem. One possible solution is to say, okay, we have to take one number. Well, yeah, so I'll just like jump to the solution, I guess. We're going to node split, so we'll have 4 copies of each node. And the idea is we're going to take this path, but we have like the sum of values. So we're adding these. And then we subtract out the minimum, or subtract out the maximum. and then add the minimum. Instead of saying this, what we could say is we subtract out whatever we want and we add whatever we want. If we're trying to minimize our cost, the thing that we'll subtract out, we want it to be the maximum value, right? That's the best thing to subtract out. And then subtracting out the minimum will be, or adding the minimum will be the best thing we have to add if we force ourselves to add some edge. So that's the idea. Yeah. So instead of making this be the maximum and minimum, we'll just say it's just some edge. Okay. So now, here's the idea. We have to take we've got some graph. At most once, we get to take some edge for free. And then exactly once, we have to take some edge, but its cost is doubled. So, yeah, that's the idea. So what we're going to do is we'll make 4 copies of each node. This first copy will just be the copy if we haven't taken an edge for free and also haven't taken an edge doubled. This will be if we've taken an edge for free but haven't taken one doubled. This will be if we've taken one doubled but not for free, and this is if we've taken both. So we have these 4 copies for each edge, and I'll just draw another node here. Now, every time we add an edge to this graph, we're going to need to add 18 new edges. Sounds like a bit much, but we add an edge from here to here both ways. So we could just take this edge normally. We could add an edge here and here both ways. And this means no matter what we've done with having taken the max or the min, if we want to, we can just not use this edge as a special edge, just use it normally. And we can go in both ways because it's bidirectional. All right, the next thing is all of these have like a normal cost. So these are just the cost of the edge. The other thing we can do is if we want, we can make this edge free. So this is like, this is free and this is times 2. This one's free, this is times 2. So if we haven't taken a free edge, then we can take an edge for free here, and then we will have taken our free edge. Also, if we've taken our times 2, we can take the edge here, and then we'll have taken our times 2 edge. You can also go from this node to here, and this node to here. Because, so this is one way, one directional, this is one directional. Yeah, so from each edge, you could like take your first free node. That's these edges here, the green edges. All the green edges have cost 0 because they're free. So that's your one free edge that you get to take. That essentially puts you in a new copy of the graph where now you've taken your free edge. So you get to jump between copies of the graph for taking this edge for free. Yeah, okay. The next thing is you can do it, I'll use a different color here, but you could do an edge that you pay times 2 on. It's the same sort of idea. You would go from some node to the node below it in the other graph. So you would take like this one here, or you could take, if you've already gotten your free edge, you could take this one here, or you could go like this. Oh, sorry. Like this, or like this. So that corresponds to, you take your times 2 edge, which gets to put you in this new, you're on the bottom half of each node now. Or each like meta node. And then finally there's one more, which is, you can take both your free edge and your two-way edge. Yeah, you can take both your free edge and your two-way edge at the same time. That's this here or this here. So you can go both down and left, or both down and right, and that's in red. The cost of that is just equal to C. So the cost of yellow is times 2, cost of red is just C. That's it. So those are all the edges you add. It's a constant number. I think in total it's 18 if you count both ways, right? We have 4 white, or we have 8 white. We have 4 green. We have 4 yellow, and then we have 2 red. So yeah, 16 plus 2 is 18. I'm probably in the way here, but yeah, in total you have 18 different types of edges. So it's 18M, and then you run Dijkstra's on that. And now we're just running Dijkstra on a normal graph. And that's the idea. So yeah, that TLE is for me in Java, and I don't know how to speed it up. So I kind of just burned lots of time on that. Now, to be fair, like I burned lots of time on other stuff too. Like in particular, my problem C took way longer than it should have. And then problem D, I had implementation issues. And then problem A, I also misread. So really just like all around, I did very poorly. And it's probably because, I don't know, maybe I'm a little rusty. Maybe I haven't done Codeforces around in a while. So that could be the case. Maybe I just got unlucky. Who knows? But yeah, so rough contest for me. And it looks like lots of people had issues with C by the fact that it had over twice as many submits as solves. And I don't think it was really that bad of a problem. Like I think lots of people had the potential to solve it, but just had issues. Maybe it's not too unusual because the same thing happened with F. So maybe lots of submits were wrong answers. I'm not sure. Maybe it's possible for E. There's just a way faster solution too. So I don't really know. Anyway, that's all from me. Hopefully this was at least somewhat helpful. And yeah, that's all. Hopefully if it was rated for you as well, you get a good rating boost. All right, have a good day. That's all, and goodbye.